But before we get there, let's start from the beginning. I have a little story to tell you, and in order to do so, I would like to try to convince you that we are very close to a space astrometry revolution as well. We are going to do so starting from the origin. And in order to tell you what the origin is, let me bring you back in time. Long Gilliland brought you back in time some 20 years yesterday. I'm going to do a 71-year leap back and tell you about the discovery of planetary mass companions orbiting 70 Ophiuchi and 61 Cygni, two nearby solar-type stars, that were found by astrometry using ground-based time series measurements. And at the time of the discoveries were hotly debated because they were being the first evidence for the existence of planetary mass companions orbiting other stars. And as you can see in the literature of the time, in important Nature papers discussing the opinions of famous astronomers like Halpern and Jeans, you can clearly see that the debate on how the heck they could have formed in the first place and the possibility of determining the fraction of stars with planets at the time was already ongoing. Now, the question for you is, why is that nobody seems to remember these discoveries? Sorry. Well, there is one good reason. Well, actually, two good reasons. First of all, at the time of the discoveries, nobody really cared because it was a bad time, as you can see the dates. People were unfortunately busy doing other things. The most important issue is that those discoveries were bogus. History of astrometric discoveries of planetary systems is long, is almost a century long, and is full of tragic events. The hope is that things are going to change very soon. The reason for this set of dead bodies in astrometric discoveries left along the road is primarily due to the fact that you have to realize what is the sensitivity of the instrument you want to use in order to detect the effects of an orbiting planetary mass companion around a star if you're trying to measure the orbital effect on the star in the plane of the sky. Just like the spectroscopic technique with Doppler measurements had to leap 3 orders of magnitude in order to become sensitive to terrestrial-sized planets with better than 1 millimeter per second precision, which is the state of the art today, starting from the kilometer per second precision of adequate for stellar mass binary companion measurements. Astrometry has to do the same. The milliarcsecond state of the art precision set by Parkhurst 20 years ago is not nearly enough to even touch the tip of the iceberg of the exoplanet population, even for the most massive giant planets. You have to do at least a couple of orders of magnitude better, and this is exactly what Gaia is going to promise to do. In fact, Gaia is not just only beginning to promise, it's started. We are 6 months into operations. Gaia was successfully launched in December 19th last year. And 6 months into operations, the science is about to start. The commissioning has been ongoing and is about to end. I will tell you a little bit about that. Gaia, as I told you, will give you a 2 orders of magnitude improvement in positional measurement accuracies for approximately 1 billion stars, down to the 20 magnitude limit of the survey. It will capitalize on the way Hipparchus worked, using a scanning law to essentially visit the whole of the celestial sphere within 6 months and repeat this set of measurements through its 5 years of nominal mission lifetime. The scanning law pattern will provide a very uneven distribution of observations in the sky, with some regions extremely well sampled, with more than 200 measurements in 5 years, others scarcely sampled, with less than 40 measurements in the same time span. The average in the sky will be approximately 70 observations. Gaia comes with the largest focal plane for space devices ever built. It will collect in its astrometric part, astrometry. It will gather photometry in a blue and red band bands, and it will also collect spectroscopic measurements and will derive radar velocities. So the three combinations of these measurements are going to give you ultimately information on all sorts of interesting issues in galactic and stellar astrophysics that you can think of, as well as exoplanet science. I told you that we are about to conclude commissioning. There's a lot of very good news. First of all, Gaia started off much better than Hipparcos and got inserted into its Lycus orbit in perfect timing, even a little bit ahead of time with a little bit of fuel savings. So there is a tentative estimate that everything being nominal, it can go for 10 years rather than 5. And there's a list of very good news that I can give you here. I won't go into any of these details. I want to certainly highlight the fact that the DPAC, the Data Processing Analysis Consortium Operations Team, is calm and competent, so everything is under control. Well, not really everything. There are a few issues. Many of you may have heard that the grapevine has leaked something about concerns on the Gaia performance. There are issues. Some of these, the ones that I'm listing here, have been understood more or less, some better, some entirely, some not entirely. For example, Gaia was found out to be almost 3 magnitudes fainter as seen at L2 than expected. This has consequences because there is a ground-based observing program that is monitoring the position and speed of Gaia essentially on almost a daily basis. This is a set of measurements that are fundamental to reconstruct eventually at the level of the fine structure of the data reduction, the global sphere of stars observed by Gaia. And this issue has already been accounted for. And instead of using backyard style 40 to 80 centimeter telescopes now, we're moving to the 2 meter class observing devices from the ground. Many of you certainly have heard about the loss of throughput in Gaia with the possible deposit of icy material on some of the mirrors. There have been already 2 decontamination campaigns that have tried to get rid of the problem. The problem has diminished, but then has come back. It's not entirely eliminated. There are provisions for a further decontamination campaign by heating up specific elements of the spacecraft to try to entirely eliminate the issue. I will tell you about the stray light last. 2 more issues have been identified that were not expected. First of all, there's a lot of meteorites that are actually hitting the spacecraft in probably a couple of orders of magnitude larger amounts than expected. This has consequences, again, on the level of fine structure calibrations when you are reconstructing the attitude of the spacecraft. Again, these things are being taken care of in terms of additional calibrations. There is an angle of 160.5 degrees between the 2 Gaia fields of view, and there is a device on board that monitors very accurately potential variations in this basic angle. Again, the correct monitoring of any variation in between the 2 lines of sight at the several picometer level is a fundamental element at the level of data reduction to provide you the microarcsecond astrometric precision that everybody would like to achieve. The basic angle variations appear much larger than expected, but again, this is something that can be possibly entirely modeled at the level of additional calibrations. The stray light is unfortunately something that will likely not be modeled. We uncovered stray light entering essentially in all sides in all regions of the focal plane through unknown paths, and the problem is apparently due to potentially design of the sun shields, and the sunlight is actually scattering off from the edges and entering at some level increasing substantially the background for faint stars. We will likely have to live with that. There is now a preliminary estimate of the scientific impact of this of the stray light in Gaia measurements. As you can see from this table, the initial end of mission estimates, depending on the magnitude range for the various values that I see here, don't seem to be significantly affected when you go down all the way to 15 magnitude or so, and this is true for astrometry and photometry. This is a completely different matter for the spectroscopy. So in general, assuming that we can cope up with the various issues that I have outlined, the stray light can be probably only a minor problem for bright stars, in summary. There will be one additional impact on the extra commissioning time that has been spent for more than 3 months. The initial data release scenario that I am listing here as outlined in this way will change for sure, at least the level of the first data release that will be postponed by the order of 6 months. So expect the first Gaia data release by the middle of 2016. I will skip the next steps and fall briefly into the final discussion that I'd like to have with you, which is what is Gaia going to give you in terms of potential for exoplanetary science? Well, keep in mind the reference number here, which will be of the order of several tens of microarcseconds for bright stars. Bright stars are those for which essentially you are dominated by systematic calibration errors in Gaia measurements. Divide that by 3 because this is per CCD, and you have the order of 20 microarcseconds single measurement precision. This number, which will be hopefully the one that will be achieved in the bright star regime for Gaia, will allow us to carefully model planetary orbits in both for single and multiple planet solutions within the Gaia Deep Arc pipeline. In the scheme that I show you here, we will actually try to fit models with different philosophical approaches, both the genetic algorithms and Markov chain Monte Carlo approaches, taking, for example, into account the lessons learned from radar velocities as far as complex models, in particular multiple systems, are concerned. 1 second on the possibility of determining transiting exoplanets candidates through Gaia photometry. There is a poster by Brandon Tingley out there, so I won't go too much into details. There is essentially the potential for Gaia to determine maybe thousands of transiting giant planet candidates with short periods, with some caveats that I show here. I won't go into details. You can talk to Brandon for additional details. In the last couple of minutes, let me give you a very quick snippet of what Gaia can do for you, as seen particularly in synergy with the other planet detection programs. As you see from this graph, which is the classic discovery space and planet mass as a function of semi-major axis, Gaia typically will detect things above these 2 curves, which means, if you look at the mass and semi-major axis scales, implies giant planets, Saturn mass around the nearest stars, if best case. This is not very interesting if you're looking at terrestrial planets, certainly, but the sheer number of objects to which Gaia will be sensitive, for which Gaia will be sensitive to planetary mass objects, would be of the orders of millions when you start combining F, G, K, and M dwarfs. And the final outcome of this exercise is that probably you will be looking at an ultimate catalog of maybe tens of thousands of new detections, new giant planet detections with Gaia. This will certainly allow you to look very much in fine detail, for example, at the dependence of giant planetary frequencies as a function of planetary properties, such as stellar mass and metallicities, as I show here. It will even be possible to detect planets around brown dwarfs, if you believe so. If you look, for example, at the third nearest systems to us, Luman 16 AB, The the companion sensitivity curve for Gaia, estimated for Luhmann 16b, tells you that it should be possible to discover objects smaller than the mass of Saturn around this very nearby brown dwarf system. One last minute, and I will breeze through a couple of slides outlining some of the potential connections that you can make using Gaia data and photometric, spectroscopic detection and characterization techniques of any type that you may desire. For example, in direct imaging, this is very recent ongoing work. We are looking at the possibility of combining information coming from acceleration in the motion of stars induced by long period companions with a direct image obtained by sphere that actually provides a projector separation value. And in the case of a very famous system, Beta Pictoris, the expected acceleration that will be seen in Gaia astrometry is very large and should be pretty obviously detectable. And these are the constraints that will come from a simulation of the expected masses of the companion compatible with the astrometric values and the present-day estimate of probably best estimate of approximately 7 Jupiter masses for the companion to Beta Peak. One last second on a couple of additional synergies. I'm gonna eat up in the question time, sorry. You will see astrometry of Gaia combined with other velocities existing today and coming tomorrow, both at infrared and the visible wavelength, to improve the architecture of planetary systems across a range of planetary masses and orbital separations. The combination of the two techniques will be fundamental to, for example, understand and improve the characterization of dynamical stability of multiple systems. Gaia may even determine potentially transiting systems that are actually at wide separations, let's say intermediate separations, maybe a significant fraction of an astronomical unit or larger. This will be done this would happen whenever Gaia will measure inclination angles close to 90 degrees, with uncertainty maybe of a couple of degrees. These objects will become potentially very interesting for follow-up from the ground to possibly identify them as actually cold giant transiting planets, and a class of objects that essentially does not exist today. One last on the potential, as I promised, to measure very accurately the radii of stars thanks to very accurate parallaxes. Let's take the example of the Kepler field. The exercises on the determination of planet frequencies as a function of stellar properties in the Kepler field essentially relies on the entire lack of knowledge of parallaxes for stars there. So in the Howard-Dahl exercise, where you, in each beam or in each cell, you put a given number of stars of given properties reflected in the properties of the detected transiting companions, detected transiting candidates. If you get the stellar radius and mass wrong, obviously stars will move around in these cells, and the estimates of planet frequencies will vary significantly. Gaia will do a very fine job in this prospect, and it will provide you with the exquisite few percent level parallaxes for all stars in the Kepler field, both the ones with candidates and the ones without as reference samples. And so this will allow you to revisit very significantly the properties of the planetary systems, validated, candidates, or confirmed, and thereby infer much more accurately the frequency of existing planetary systems all the way down to terrestrial planets and possibly even habitable ones. And I conclude here.
Thank you very much. So, sorry, it was very interesting, and you gave a few highlights on what we can expect from Gaia, but maybe time just for one question. Yes.
So the candidate transiting planets you'll find, given there's going to be a median of 70 observations per star, presumably there will only be a few in transit. Will the orbital ephemeridese be good enough to try and follow these things up from the ground easily?
This is ongoing work. We are looking, for example, at the possibility of determining accurately the ephemeris of candidate transiting companions at intermediate separations around the nearest M dwarfs. There is a work that is essentially expanding on the one that we published recently this year. The initial estimates that we are seeing is that when the orbit is measured relatively accurately, so you have uncertainties in the inclination angle of 2 degrees or less, the expectation for the ephemeris prediction can be of the order of a couple of weeks, which is on orbital separations up to 1.5 AUs or so a couple of years of period. And this seems rather encouraging for the prospects of potential follow-up from the ground.
Okay, thank you very much.